At the start of this series of little talks, I said that when we talk nuclear power, we are essentially talking power from nuclear fission, the splitting of heavy nuclei. However, there is another potential source of energy, namely nuclear fusion. And nuclear fusion involves the fusing together of light nuclei. It is an important source of power because it's what sustains life on Earth. It's the process that goes on in our sun. And basically what happens is that a couple of hydrogen atoms, each mass 1, four hydrogen atoms, each mass 1, fuse together to form a helium atom of mass 4. If you add together the weights of the 4 hydrogens and you weigh the resultant helium, you find that the helium weighs a bit less than the 4 hydrogens. There's a loss in mass involved, and it's that loss in mass, that mass is turned into energy according to the Einstein equation, E equals mc squared. And this is the process that goes on in the sun. We know on planet Earth that solar energy arrives at the upper atmosphere at the rate of 1.37 kilowatts per square meter of the world's disk. We are 150 million kilometers from the sun, so if we worked out the area of a sphere of radius 150 million kilometers, or if you like 150 billion meters, we could work out the area of a sphere on which the Earth lay 150 million kilometers from the sun. If we multiply that by 1.37 kilowatts, we can actually compute the power of the sun. Now, I've done this little calculation, and what I've found is that on planet Earth we absorb, in round figures, about 1/billionth of the energy emitted by the sun, and that amount of energy is enough to power all the life processes on Earth, all the photosynthesis and keeping all the plants and animals alive. So this is clearly a powerful source of energy, and back in the Second World War, when the Americans set up the Manhattan Project, the actual weapons design lab was located in Los Alamos in the western United States, and it was directed by a bloke called J.R. Oppenheimer. And on Oppenheimer's staff, he recruited a very bright Hungarian emigre called Edward Teller. And Edward Teller became convinced that thermonuclear fusion, the fusion of light nuclei, could produce vast amounts of power, even more than fission, and therefore it would be possible to build a super bomb, a hydrogen bomb, a thermonuclear bomb. And he was very obsessed with this, to the point where he didn't really make much contribution to the atomic bomb, but he certainly did when the Americans decided to build a thermonuclear bomb 10 years later. Now, this source of energy goes on in the sun and other stars, and people after the Second World War thought about, could we possibly harness this process on Earth? Now, this is fraught with difficulty because the temperature in the sun, even at the surface, is tens of thousands of degrees Celsius, and to initiate a fusion reaction, you probably need to get an amount of material up to perhaps even 1,000,000 degrees Celsius. Now, how do you contain material that sort of temperature? That's the crucial question. It was solved by some British physicists working at Harwell in the 1950s. They realized that if you had a tubular structure, and around this tube you wrapped electrical conductors and then passed a very powerful current through the coil, you could produce an electromagnetic field inside the tube which would pinch any charged particles into a narrow strip in the center of the tube, and it wouldn't thereby touch the surface. if you've got stuff at 1,000,000 degrees, you can't have it touching anything, because the most refractory material we have known to technology is the element tungsten, which melts at 3,600 degrees Celsius, well below the sort of temperatures we would need to achieve thermonuclear fusion. And at Harwell, they built a device called a Zeta Device. This was a Zeta project, and it consisted of a sort of an oblong tubular structure around which they wrapped these coils. And they found, in fact, that they could contain high temperature plasma. If you heat hydrogen gas up to tens of thousands or hundreds of thousands degrees C, the electrons are stripped away and you've got a mass of protons, positively charged protons. And this gas is called a plasma. And this electromagnetic field effect will pinch it to the center of the vessel and prevent it from touching the sides. So you can actually contain this gas plasma at very elevated temperatures by passing powerful currents through the coils. They did the calculations, and basically they couldn't get enough material to a high enough temperature to get a self-sustaining thermonuclear reaction. They weren't the only people addressing the problem. It was being looked at in the States and also in the Soviet Union. And the Soviet Union, they had two very bright physicists called Igor Tamm and Andrei Sakharov. Andrei Sakharov was the bloke eventually who designed the Soviet hydrogen bomb, and he came up with the idea of a toroidal vessel, as shown in the figure. It's like a donut, and again it was surrounded by electromagnetic coils to produce the pinch effect. And using this design and some refinements, they cranked the temperature up even higher than the Harwell scientists had managed to do. However, they were still limited by the amount of power they could put through the coils, because if you stuff enough electrical energy through any length of metal, it will eventually melt. It'll fuse like a piece of fuse wire. And they weren't able to generate sufficiently high magnetic fields with the current levels they were using. However, in the 1980s, a very significant advance occurred in the science of superconductivity. A conference was convened in America, and then just before the conference took place, one of the researchers, either in America or Europe, discovered the phenomenon of superconductivity. They discovered it could be achieved in ceramic materials rather than metals. The phenomenon was discovered 100 years or so ago by Kamerlingh Onnes, a Dutch physicist, who found that if you cooled metals down to near absolute zero, minus 270 degrees, you could then put a current in, and the current would continue to flow around the circuit even if you took away the voltage. This is superconductivity. The metal becomes superconducting. It has literally no resistance. Now, once the scientists had discovered you could do this in other materials, that conference, where the initial registration was 200 or 300 people, eventually 7,000 people turned up to hear this news, and it was great news because it had all sorts of implications for research in all sorts of areas all over the world, and they dispersed, and people thought, well, we won't look at metals anymore, we'll start looking at ceramic systems. And the result has been, over the last 20 or 30 years, that we can now achieve superconductivity at temperatures well above absolute zero. It's a much more practical proposition, and the effect is that we can build things like the Hadron Collider at Geneva, and we can accelerate particles to very high speeds, and of course in these toroidal tokamak devices that the Russians started, we can generate very great electromagnetic fields and pinch effect, so we can contain a much bigger mass of plasma and get it up to much higher temperatures. Now, we've now reached the stage where we can actually put a pulse of power into one of these tokamaks and get slightly more energy out of it than we put in. So the last device was built at the Column in Oxfordshire, the JET project, the Joint European Torus. They reached this point 20 years ago, and they're now building a new device in France which will enable them to get even higher temperatures and higher energy densities. If there is results from this research are satisfactory, then eventually we can build a thermonuclear power station where we generate significantly more amounts of power for a given input. Obviously, it's a process that needs a big energy input, but potentially we can get huge amounts of energy out. Why is this important? Well, we've seen that fission reactions rely on uranium. We have to mine uranium. The stocks of uranium around the world are limited. We mine it in Kazakhstan and in Central Europe and Africa, in Australia and various other locations, Canada I think. The total amount mined each year is of the order of 45 perhaps to 60,000 tonnes. Now, to put that into perspective, a modern large blast furnace, we shall shovel 60,000 tonnes of iron ore, limestone and coke into there every 2 hours. So globally, 60,000 tonnes is a small amount of material. But of course we've seen that fission reactions generate radioactive isotopes which then have to be stored. What about fusion? Well, if we can fuse light nuclei together, we can get the vast amounts of power, and we don't split atoms, we fuse them. We don't produce a lot of radioactive byproducts. So potentially, it's a much cleaner industry in terms of the waste produced. We will generate a little bit of radioactivity, I think, but it'll be very small compared with the conventional power industry. The material we use to do it, well, we don't need to mine uranium, we just need hydrogen. On planet Earth, we've got 1.4 billion cubic kilometres of water, a source of hydrogen. So potentially, the material we need to sustain fusion is unlimited, and this is the ultimate attraction in energy terms. We wouldn't be depleting a limited resource as we are with uranium. We wouldn't be producing a lot of radioactive byproducts, but we could potentially produce vast amounts of power. It wouldn't be cheap. Obviously, these devices would be very expensive to build, but power could be generated in almost unlimited quantities. So that's the hope for the future, thermonuclear fusion based on the fusion of light nuclei.